Can you see the screen well?
Yes.
Okay, awesome. All right. Thanks a lot for giving me this opportunity. Really excited to present the model here. So I'm going to kind of start a little bit from the background of the company. Go to the next slide. So American Eagle Outfitters, generally I'll refer to it as AEO. It's a specialty retailer company, mainly operating in US and Canada. We have about over 1,000 stores in various countries, around 81 countries, and then it's mainly in the fast fashion. We are mainly serving in the fast fashion business. So the people who are from US must have heard about AEO quite more frequently. And from the perspective of distribution network, in US we have around 3 distribution centers, and then recently we have acquired a 3PL called Quiet Logistics. So we also operate via in-market nodes in major metropolitan cities. So the one DC is around 1 million square feet. So our footprint is these 3 main DCs and smaller nodes. All of these nodes serve as omni-channel nodes. So if you think about operations, all of these nodes kind of serve as pick, pack, and ship type of operations, one way or the other. And then there are various companies as a part of AEO family. So the bottom line here, if I go back to slide, this one kind of shows some of the main brands. American Eagle and Aerie are one of the main brands in the United States and Canada. So how we came to kind of use FlexSim and leverage simulation modeling in different aspects of our processes. So this year in Q3 we got some licenses to use FlexSim, and one of the main purposes to find the areas or the processes in our network, and especially in the distribution centers, to simulate and from the perspective of any changing or any improvement efficiencies, test it in the simulation environment, see the impacts, and then kind of implement it. So just traditional way of implementing any simulation model. So it's mainly concerned with the flow modeling of products inside the DC, so within 4 walls of the warehouse. And what I'm going to present today here is a carton packing process. So the simulation model that I worked on to basically, which is the model to simulate a process where we pack cartons, and those cartons are shipped to the stores to fulfill their inventory requirements. So we have around 1,000-1,200 stores, and then each of the stores have their unique requirements that has to be fulfilled. So whenever you walk into a store, you'll see all the display quantities and all the SKUs sitting inside the stores. Those are fulfilled from the DCs, and we have an operation in the warehouse which kind of caters to that demand. So I'm gonna go through just the overall high-level process here, how it works in the distribution center. So from like first stage in doing this process is picking. So there are units that are either units that gets picked inside a tote, and then tote goes to carton packing operation area, or we receive we also send entire carton of a specific SKU if all the units will be fully consumed in the area. So one of these two would be traveling on conveyance. So they go to this carton packing area. There is a 5-to-1 merge on conveyance. So you'll see a lot of conveyance in this model, and then a lot of product flow in this model. So there is a merge point. After the merge point, different cartons or totes divert to their own specific lanes. And on those specific lanes, there are packers who are picking units out of the totes or cartons and putting that into a store carton. and that stored carton is specific to a store. And then once we have enough units in a carton, that gets shipped to a store. This is high-level process overview. So the main problem in this, which we wanted to kind of answer from simulation perspective, is to reslot this entire area. So when I say a tote or a carton diverts to a packing row, once I show the model view, you'll kind of it will make more sense. But every row or a lane where a packer is along the side where a packer is packing units into a store carton has fixed locations where there are stores which are slotted, and these stores cannot be changed dynamically. It's a fixed slotting system. So when we want to make a change in this entire system, it's around 31 packing rows, and on each packing row there will be multiple store slots. If you even want to make one change, we have to go through a downtime of around 36 to 40 hours, make all those changes, and then again go live with the newer type of slotting mechanism. So the main question I was trying to answer with this simulation model is, how can we test those different reslotting scenario in the simulation model, look at the gains that we get out of different scenarios, and if it really makes sense from the benefits perspective, then go about implementing it. So we minimize the disruptions in the operations, and we also minimize the downtime that that DC has to take. Just some as is and to be process information. The current mechanism to reslot was, build different scenarios in Excel and then only test it on a unit volume level. So the number of units that will enter the system and the number of units that will exit from the system. So that doesn't really give any view on what will be the impact on total conveyance utilization, if there will be if there will be a blockage on the conveyance, if there will be a blockage on the 5-to-1 finger merge, 5-to-1 merge, or if there will be any issues in totes getting backed up and then shutting down the entire system. So generally it has been used more from the Excel perspective, and then there has been instances where you have to do it again because the results that you expected didn't really come to fruition. So from the model perspective, I kind of focused on some of these factors to be built intricately, and then some factors to be only built on a high level, so that the model is actually addressing to the flow problems versus some problems that are not very important. So this model was developed on a CAD diagram. It's basically in the DWG file of the DC. If you see this diagram, this is the area. It's not shown in detail, but this is the area where we perform the picking, and then this is the model. It is built on the top of the existing conveyance diagrams. So you can see a lot of conveyance here. So this is where the packing happens, and then the finished cartons are kind of they go to the shipping area, and then they get loaded to trucks and then get shipped out. So the flow is in this way, and I'll be kind of going in detail on this packing operation in just some minute. Just overall packing process information, as I was alluding to. So there are a lot of components in this. Before building the model, this was my first project, so I had to kind of really understand what is the best way to build a simulation model and how do you keep it as modular and as schematic as possible. Because earlier when I was kind of practicing some problems, I would just build a model and then realize that okay, this cannot be scaled very well. So this is just high-level view of how many objects were in the existing model and what I had to model. Some index points. There are 31 packing rows, so 31 packing conveyors. There are 3 zones on each packing conveyor. So these 3 zones are where the operators work. So one operator is working in one zone. So every row has 3 zones. So every row has 3 operators kind of packing units from tote to a store carton. Number of slots on each rows. The induct conveyors, these are the divert conveyors, kind of the same thing as the packing rows. So these induct conveyors merge into packing rows. There are once a tote goes down a conveyor and it gets fully processed, there will be some units which will be left in the tote. That tote has to again travel back on the entire sorter, come down, and then again divert to another row. So one tote can divert to multiple rows based on the need. So if there are 3 stores which needs one, there are 3 stores which needs one SKU, one tote will have to go to all those 3 packing rows to fulfill that need. So there are different outbound conveyors, and then once a store carton is packed, that packed carton will exit from one of the outbound conveyor to go to a shipping area. So this would give you kind of like a good overview on how the model is structured and how the area is structured. So in the real life, there are 4 conveyors, which are induct conveyors. So this either totes or cartons, they travel from picking area and then they enter here. But I've only modeled 2 conveyors, so I have merged those 4 conveyors into 2 based on different based on different flow types, from just a simplicity perspective in modeling. So this is the induct area where new products would be entering. So new totes or new cartons will be entering. They travel this conveyance and then they merge here with some recirculating totes or some totes which has been processed. So if I kind of show you guys the flow, a new tote will travel in this way. It will circulate here. So it will go through this conveyance to circulate here and then go all the way around. It will get scanned at one of the point here. And that scan will determine where that tote has to divert in one of these 31 packing rows. So then that tote or a carton will travel this row or travel this sorter. It will get diverted to one of the conveyor. And then this is a this is on the floor level 1. So once it gets diverted, it's going to go down on the lower floor where packers are working alongside a packing lane and then finishing the process. So kind of finishing the packing process. Once that tote is finished working on that specific packing row, it exits from this black conveyor that you see all the way down. And there are too many objects in this model, so I couldn't really zoom in. So it exits from one of this conveyor and then travels all the way to this area. And there is a plane which is not showing the conveyance here, then comes back and then travels all the way around on this external loop, which goes around here, goes back, and then again merges here. So that is kind of like a tote or a carton flow. And this area that you see here, this is where, from the model illustration perspective, finished cartons are being stored. So I have added like a bunch of queues here at the end, around 16 queues. And then these queues will hold finished cartons. And then there are horizontal queues on which you can see here in black color. They will hold empty cartons. So you wouldn't see any packers working in this area because of just the model, like number of objects in the model and the runtime of the model. But most of the process is kind of like managed by the process flows. 1 second. So just the modeling approach here. The way I had to build the model, I'm kind of going through that process. I did some metric selection. Then there is physical flow building, and then there is process flow building, and then there is some type of data structure modeling. So I'm taking data from the raw warehouse management system, converting them into different tables, which are then loaded to FlexSim. And then once it is loaded to FlexSim, that's when I'm running 1 day of total volume to test different reslot scenarios. So this first one is the metric selection. When I started the project, like I was kind of a little bit lost because the project seemed too big to be implemented. So I really wanted to focus on the things which were critical to be modeled, and I just did a value effort metric to make sure the amount of effort that I'm putting to build one feature in the model is valuable enough. So one question I was running into is, should I model the operator process where an operator is going to a tote, picking a unit, and then putting that inside a box? The operator modeling would, be helpful to measure operator productivity, but it would require modeling 75 operators. So the model will get quite humongous. So then I didn't go into that details. I kept the model at a flow level, and that's what was more important. One thing that I focused while building the model, I got some benefit by working with a person who has experience in simulation modeling. So I used a lot of model tree to build the model. So I built one object and then copy pasted it multiple times. So that helped me scale the model really fast. Because if you see this one area, everything is pretty standard. So I can just build one area and then copy paste it multiple times. Now I'll go to the process flow. So I have 3 or 4 minutes. I'm gonna go kind of quickly through this. There were 8 main process flows, and I'm gonna go through them real fast right now. Model initiation. When I initiate the model, it creates induct totes, so induct objects, which will be totes with units. So pick totes with units or cartons with units. That gets generated on a queue. Then it also creates empty cartons, empty store cartons. These are the empty store cartons which get packed into. So inside these cartons is where the units are placed. So that gets generated, and then there is a first row assignment. So when the tote goes on the conveyance at a scanner, it gets assigned a first row based on different tables. So from divert perspective, a photo I process here was more important to make sure if the diverts are being blocked, then a tote cannot be diverted to that conveyor. So that's something we wanted to look at from the model perspective and flow perspective. So a process flow for that was built as well, based on different decision points and things like that. And there is, as I said, once a tote gets processed on a conveyor or on a pack conveyor, it retravels the entire area. It comes back on this outer loop. It gets scanned here. This scan checks for the next row assignment. So if that tote has to go to another row, if it has to go to another divert, this scan will give it another row. Or if it doesn't, if the tote is empty, then the tote will be getting assigned empty divert, and then it's going to get colored red, and then it's going to go to that specific conveyor. So then this fourth process flow was to really build the packing logic. So when the tote comes to a packing zone, how is it getting consumed out of, and how is the packing process being worked on? I use a lot of lists to build all these process flows, so that has been really helpful in kind of generating orders, in storing inventory, and then finishing cartons and things like that. Same thing, creating store orders. So the store order has to be created, and then that's what gets used to pull the units from the totes. This was one of the main process in this model where empty cartons are pulling units from the tote. So when the tote comes to a station, an empty carton will have a pull query, and then once the unit gets available, it's going to pull from the tote. Just some process flows, extra process flows. So, and then this 4:1 merge, I kind of used the gap optimizing merge controller to make sure the logic I had to build was captured in that. The data structure, I'm sorry, I'm running a little bit faster through this, but I had to use Python to kind of do some data manipulation to make sure that the data I'm getting from raw system is usable for FlexSim. So and then all the dashboards were built inside FlexSim. So some things that we were mainly concerned to look at is how many average diverts we have per tote. And if we have more number of diverts per tote, that means it requires more time to finish a packing process. So this is what we are trying to minimize in different slotting scenarios. And then also number of amount of time it takes to fully consume a tote. So some basic statistics which were important to kind of test reslot scenarios. Different pack zone states. So if every packing row has 3 zones, and how many times is it being idle or being processed on, things like that. How many cartons, how many finished store cartons throughput we have in a 24-hour model run, and 4 to I block states and things like that. Some results that we observed from this first implementation of the model was there were different slotting scenarios that were tested in the model. Even and then it was found that those scenarios would actually work against the flow. So first, I mean, this model helped to not implement something. At the same time, even though we didn't make a lot of, I would say, we did not implement the change. It also helped us to save all the extra efforts that we had to take to kind of redo the same thing. And for me, one of the main learning from this modeling was to build the model in a more stochastic way. So currently my model is built on the actual real life data of one specific historical day. So it's all deterministic data. I'm going to use some kind of distributions to generate totes and arrival times to use it in future. So that is more scalable and more representative of the model of the real life process. That's it from my side. I had to kind of go through that real fast, but if you guys have any questions, feel free to ask. Yeah.
Yes, we actually have quite a few that have lined up. So let's get started here. How many SKUs are being managed with reslotting? Was each SKU modeled separately, or were they in groups to simplify the modeling?
So the number of SKUs, it really differs from day to day. The reslotting is mainly for the stores, not the SKUs. So total number of stores are around, in one reslot, we would touch around 7,000 to 9,000 store slots. And all of those slots will have to get changed. So one store will move from one packing row to another packing row. So I hope that helps kind of the question that somebody has asked. It's not SKU that we are reslotting, it's the store locations that we are reslotting to.
Thank you. Let's see. Did you have this model automatically pull data from a warehouse management system? And if so, can this model pull data real time?
No, so right now it's all manual extraction. So the queries are built to extract data from warehouse management system, but then it's being saved on a local drive, and then new tables are being created to be loaded inside the model. So it's not connected to the WM system right now.
Thank you. Why would using 75 or as many as needed operators complicate the model? From the model, it seems that the tasks are always the same and the variables of the model can be stored in the model, which means you could have operators as a resource or a list.
Yeah. So that's a very good question, and that's the question I was asking myself. Only reason I did not do it right now is one, the model is working on this deterministic data. So I'm using exact timestamps in the real life. So my current model runtime is around 6 hours for 24 hours of volume, 24 hour of volume. And I haven't optimized the model. So I just thought that if I add operators in this model, one, it will be difficult to see in 3D model. And second, it's going to take more resource to run the model because it's being run on a laptop right now. So mainly model runtime was the concern.
Okay, thank you. Another person asked if there's any way you could return to slide number 21 and explain it. I think that may have been one of the slides that you had to brief through really quick, just at a high level.
Yep, let me go back. '21. Okay, I'm gonna present if that's fine.
Yeah, of course.
Okay, was it this slide?
Yes, I believe so. Yeah, that's slide 21, yeah. Correct?
So yeah, this is slide number 20, and I have slide number 21. I'll explain both. So when I said pack zones, I'm sorry I had to breeze through it, but one packing row has 3 pack zones, and I have used stations here. So when the tote arrives to, there are stations A, B, and C. So when a tote arrives at station A, that station A will be assigned different stores on that specific packing row. So if let's say store A has demand that is coming from that tote. So if store A needs a SKU 1, which is available on that tote, that store is going to consume that 1 unit, and then that 1 unit will be put inside that store slot. So that tote is going to have some demand on this zone A. Once the demand on zone A is fulfilled, that tote is going to go to zone B. Once the demand on zone B is fulfilled, the tote is going to go to zone C. And once all these zones are fulfilled from the requirements or demand perspective, that tote can be either emptied out, or it can still have some units left inside the tote. And then it's going to transfer to this black conveyor. And this conveyor is going to go back, going to take the tote back on the packing system, which you saw on the overall diagram. So this conveyor is what takes the tote back into the system, and then all of those totes merge together on one conveyor, and again come back to that merge point, that 5:1 merge point. So I hope this helps kind of explain it a little bit better.
It does. Thank you.
Yep.
And then let's see. One last question. Are American Eagle Outfitters shipping, are these all to store, or are there any direct ship to customer?
So these are this specific process is just for store shipping. This is we don't ship to customers through this process.
Okay. Okay. And then actually one more question just came in, if you wouldn't mind answering just one last question. This person said maybe they missed your explanation or misunderstood the modeling approach, but if you use exact timestamps to represent the operation time, how can you conduct multiple iterations?
So I have not conducted multiple iterations. What I'm doing in different scenarios is I take one historical day, run it through a current slotting scenario that is already in the system, already in the process. And then in the new slotting scenario, I'm using that new slot scenario, backfilling the historical data, and then I'm running that new data through the model. So what I'm changing is the slots on the packing rows, and then I'm keeping the input data same. So I hope that helps. So that reslotting is not done within the model, it's done externally. But the way I built it inside the model is there is one table which changes all the reslots on each packing conveyor. And then once that is loaded, the same data will be processed through the model, and then we can see the results.
Excellent. Well, thank you very much. It was a fantastic presentation. This is a lot of great information about simulating in complicated warehouse environments.